Hello, welcome to FM Mathematics. I'm going to show how you can find easily the integer solutions for Pythagorean Theorem. In fact, this method is so simple that you can do some of this stuff in your head pretty easy, where you just find the square of two numbers, sum them together, and you know what the square is going to be, or what the number squared on the other side of the equation is going to be. Also, you can find some much more complicated solutions for this, because this is going to be more of a general equation. So if you want to put big numbers in there, you can find how two big numbers squared is going to equal some other big number squared. So what do we want to prove? We want to prove that a squared plus b squared plus c squared, if you have a squared plus b squared plus c squared, and then you substitute n squared minus m squared for a, substitute 2nm for b, you're going to result where c is going to be n squared plus m squared, giving us n squared minus m squared squared plus 2nm squared plus n squared plus m squared squared. Alright, so what do we need to know? Really just need to know algebra. This is a really simple concept. There's nothing, no calculus required, no derivatives or some type of set theory. You could apply set theory to some of the stuff I'm going to show later, but really unnecessary. This all is very intuitive once you see how the steps work. So first, what we're going to do is we're going to start with the left-hand side, where we have some number x minus y squared plus some number k equals x plus y squared. You're going to expand both sides, where we have x squared plus y squared minus 2xy plus some number k. And then we have x squared plus y squared plus 2xy. And then we see our like terms on either side. So we can go ahead and remove our like terms. And then we end up with having a negative 2xy on the left plus some number k equals 2xy. And once we solve for k, we get what our k is. We get k is 4xy. So once we substitute that 4xy back into the equation, we get our x minus y squared plus our 4xy equals x plus y squared. Now, we're going to go ahead and let x equal some number n squared and y equals some number m squared. So when we do that, we start to see the equation forming now. We have the n squared minus the m squared plus some plus 4 times n squared plus m squared plus n squared plus m squared squared, right? Now we also recognize that 4 is a square. So we go ahead and put that to the second power and make that a 2, and then we pull it all out and encapsulate it under its own square to have our n squared minus our m squared squared equals a 2nm squared plus n squared plus m squared squared. So if you can just remember that off the top of your head, you should be able to find the integer integer solutions for the Pythagorean theorem. Now, some examples of how this works. If we have n equals 2 and m equals 1. So n equals 2 gives us a 4 plus a 1, or 4 minus a 1 rather, on the left-hand side. 4 minus 1 ends up being your 3. 2 times 1 is going to be 2, times your 2 is going to give you your 4. Then you're going to have 2 squared plus 1, where 2 squared plus 1, 5. And then you get the solution for Pythagorean theorem using integers that we all know and love. Our 3 squared plus 4 squared equals our 5 squared. One that's a little bit bigger, your 5 and your 3. So you take your 5, you square it, you get 25, and you minus your 9, which is your 3 squared, and you get your 16. Alright, and so for 30, you get your 5 times your 3, you get 15. Multiply that by 2, you get your 30. And then for your right-hand side, you're going to have your 25, and you're going to have your 9. You're going to add them together. You're going to get your 34. So, going a little bit bigger than that, your 6 and your 3. Alright, so you have your 36, you have your minus your 9, which gives you your 27. You have your 6 times your 3, which is going to be 18. And then you multiply that by 2, you get your 36. Then you get your 36 plus your 9, and then you get that 45. So now off the top of your head, you can say, well, 27 squared plus 36 squared is going to equal 45 squared. Now what's interesting to note is that if n minus m is an odd number, then the n squared minus m squared is also going to be odd. So the reason why that's interesting is you cannot actually take two squared odd numbers, add them together, and get an integer squared value. That can be proven. But you can do an odd and an even, and an even and an even. And this is how you can use this equation to get your odd and evens and evens and evens. So also if n minus m is an even, and then n squared minus m squared is going to be an even number, as you see on the top, right? 2 minus 1, that's an odd number, so we have an odd number. 5 minus 3, that's an even number, so you have an even number. 6 minus 3, odd number. All right, so now I'm never going to make a video where we don't make it a little bit scarier. So how we're going to make it scarier is we're going to generalize this equation so that you have multiple terms that are being added together and they're being squared. And they're still going to equal a square on the right hand side, and they're all still going to be integers. Now, we are going to have a summation of numbers where we have subscripts for C, where all the even subscripts are going to be negative and all the odd subscripts are going to be positive. Now, this is kind of like an oscillating parity. So we have C1 minus C2 plus C3 minus C4, and as many as you want up to Q. And it doesn't matter, they don't have to stop at an even or stop at an odd, it can be anything. You're still going to, and all those are going to be squared, by the way, you're still going to add some number k, and they're going to equal the summation of all of those terms, the C1, the C2, the C3, the C4. So this is the same first step that we did before when we were showing our calculations. Now the next step I might have to explain a little bit, because if you don't know the multinomial theorem, you're probably familiar with the binomial theorem. The multinomial theorem is if you take the power of multiple terms, what happens, or how do you expand that? The good news is that squaring a multinomial is a really simple pattern where each term under the square is itself going to be squared. As you see here, I have a c sub p squared, and it's going to be summed where p equals 1 to q. And q being that last term that was under our square. And because they're squared, they're all going to be positive. So that's easily explainable. Now, the second part of what you're going to get from the multinomial theorem when you square those terms is you take each term and find and combine them into 2, and then you multiply 2 in front of it. So just as an example, when we did x plus y squared, right? First you got to square each term, x squared, y squared. Then you got to take each of the terms inside, put them together, and multiply it 2. So x and y times 2. Therefore, x plus y squared equals x squared plus y squared plus 2xy. Now, if you were to put this in three terms, x plus y plus z squared. How do you expand x plus y plus z squared? Well, again, you got to square each one. You have your x squared, you have your y squared, you have your z squared. Then it's 2 times xy, xz, yz. So you have 3 terms all being multiplied by 2 in that case. So it's the combination of each term. You do this for as many as you want, it's going to work. If you do x, y, z, and t, x squared, y squared, z squared, t squared, plus 2 times xy, xz, xt, yz, yt, zt. So what we're going to do is we're going to take advantage of that in this, and we're going to say, okay, so I am squaring some parity. Now I'm going to separate them, where I have plus 2 times the summation, where my combinations are both going to have an odd subscript. It's also going to be plus 2 times where my combination is going to have even subscripts. So the first one, you can have 1, 3, 1, 5, 3, 7, it doesn't matter. C5, C11, that's going to be taken care of under my odd summation, and that's going to be positive. So, and then the even ones, so you can have C2, C4, C2, C6. It doesn't matter how you combine them. This is all the even ones. And again, note that that is positive. And note that if S is odd and T is even in the fourth term I have, that's actually subtraction. So it's a subtraction here. That's very, very, very important because that's what's going to create the formula. What creates the formula is when you have the subtraction. What combination ends up becoming a negative? And we're still going to have just plus k. And on the right hand side, you can see again, all of our terms together are squared. So when all of our terms together are squared on the left and the right, we can go ahead and we can nix that all automatically. That's always going to happen. Now, on the left-hand side, we have for our positives, we have two where the subscripts are odd, two where the subscripts are even. And on the right-hand side, we have all combinations of the subscripts, every single combination. So every combination where they're positive will be removed. Any combination where on the left side it's negative just turns into a 4 because I have to solve for that. So we end up getting our k, where our k is going to be 4 times this summation where s is odd, t is even, and s cannot equal t. Obviously, s cannot equal t if s is odd and t is even. I really just kept that there for good measure. Probably a little tired when I did this slide. So I go ahead and I take k, I substitute it back in, and now I'm forming the same exact steps I did before when I was doing the Pythagorean theorem. So I'm going to go ahead and let c sub p equal some number n sub p squared. And now I have a bunch of terms that are squared under a square, just like I did when I only did this with x and y, and we got n squared and m squared. So the magic happens again on the second term on the left-hand side, where we recognize that 4 is a square. And we go ahead and we take 4, we make it into, we say that it's 2 squared, and we just kind of smash it in with our n, s, and t squared, and then we encapsulate it all under a square. So now I have a summation of squares there. And on the right-hand side, nothing really had to change. It's just the n1 squared plus n2 squared plus n3 squared, however many you want to do. The whole point of this is you can make it any combination you want. It doesn't matter, so long as you follow the pattern of how we derive this formula. So if you just want to put it in summation notation, if you're comfortable with that, I like to kind of show both because I know that people coming up in mathematics may not be comfortable just seeing the summation notation. So I do like to write it out just to make it clear of what's going on. But if you were to put it in summation notation, this is how it would look, where you have the summation of -1 to the p1 power np squared, for where p is 1 to q, all that's going to be squared. You have the summation where s is odd, t is even, and it's 2 times ns and t squared is going to equal to np squared, the summation of np squared, where p is 1 and q is whatever you want, all being squared. So now let's look at some examples of this formula. So this formula, now we can find some interesting combinations here. If we pick 3 numbers, if we pick an n1, n2, and n3 only, we're going to have 3 terms on the left side, 1 term on the right. If we have 4 of them, however, we end up getting 5 terms on the left side and 1 term on the right. So the question is, can you have 4 terms on the left-hand side and 1 term on the right? So yes, you can. The formula that I created was not a general formula. It was kind of like a kind of general formula. But realistically, you can choose any combination of positives and negatives under your first square. And those combinations, depending on what pattern you choose, will create different amounts of terms on the left-hand side. And you can get 4, you can get 5, you can get 6, you can get any amount of terms on the left-hand side that you want, just depending on how you assign those parities to those numbers. So just go through what we have here, the first couple at least. 2 squared, 3 squared, 4 squared, you get 4 plus 9 plus 16, or I'm sorry, 4 minus 9 plus 16, you end up getting 11. You take 2 and 3, and then you multiply that by 2, you get your 12. You take 3 and 4, you multiply that by 2, you get 24. 12 times 2, 24. All right, for your second one, you have a 4 minus a 16 plus a 36. You put all that together, you get your first term, you get your 24. You take 2 times 4, which is 8, multiply that by 2, you get your 16. Then you take your 4 times 6, which is 24, multiply that by 2, you get your 48. Then you add all of the squares of those to get your right side. So you get your 36 plus 16 plus 4, and you get your 56 squared on the right-hand side. So, and the bottom one, I used 4 terms just to show that it does work when you do more than 3 terms. You can still just do 4. You can also do 4 terms, but again, you get 5 terms on the left as a result and 1 term on the right. But you can go through them just the same, where you have 1 minus 4 plus 9 minus 16. And then you get your 10. Then you do combinations. You get your 1 times 2 times 2, 4. 1 times 4 times 2, you get the 8 term. 3 times 2, 6 times 2, you get your 12 term. 3 times 4, 12 times 2, you get your 24 term. And then this, adding up all the squares of those, you get your 30 term. So I hope this video was interesting to you. I hope that maybe it helps you in some type of mathematics in the future. If you'd like to see more videos like this, please comment. If there's any kind of video you want me to make, if there's anything, any topic you want me to explore, I'm very open to it. I have a whole list of videos that I'm going to be making. It's going to be a slow process because some of these videos are going to be long. I'm going to try to shorten them, but some of these videos are going to be pretty complicated and require some pretty high level math. This one I just thought was kind of fun and to throw it out there. And hey, it's a good parlor trick to be able to just take any 2 numbers and then square them, add them, and then know what the square is going to be, and you know, do it in a bar. You can go to somebody and say, hey, give me 2 numbers, and then see if you can create a square and get the answer. All right. Happy mathing.